All right, so now that you all have AutoCAD working, we can start talking about what's next. The first thing you need to know is that your experience with AutoCAD will be a whole lot better if you have something like this. Okay, I'm a trackball guy, but you don't have to. I'm not saying trackball. I'm just saying a mouse. Okay, much better experience than the trackpad. I got nothing against trackpads, but AutoCAD is going to be, your experience with AutoCAD is going to be much more pleasant if you have one of these. Okay, and what you're looking for is something that has some sort of scroll wheel, and you also need a middle button. You know, it's not just to have not just left click, right click, but you need to have a middle click as well. So on some mice, that's like you actually press the scroll wheel, and that's a button. On the trackball, it's something different. I actually do like a little double click on, and then I can pan around. But your experience with AutoCAD will be much more pleasant if you can acquire a device like this. Okay? So if you don't have a device like this, that's fine. We'll get through today, but highly, highly, highly recommended. I'm stopping short of requiring it because I always feel bad making you guys buy things when you don't have money. So I'm not saying you have to. I'm just saying that, I know, it's like I already feel guilty enough making you buy the computer. So it's like that's all my conscience can handle. So I will stop short of saying you must, but I will say highly, highly recommended.
The thing is, like, I have like the normal Logitech trackball, like
Yeah.
the $25 one, but then I have to download it.
Yeah, I know, it's a pain. When you do that, it'll launch back up, and you should at that point have
Back to all the defaults. Okay? So once we're done with this class, you can do whatever you want with your AutoCAD, but for purposes of this class, like, let's all stick to the same interface. Okay? That will speed things up considerably. All right? So in this window, you've got 3 different tabs here. You've got Create, Learn, and Extend. The only one that we're going to care about at all is the Create one. So if you are going to create a new drawing, it's going to show up a bunch of templates here. And if you look at these templates, you know, they're all about, you know, doing buildings or designing cities or something like that, none of which we're going to do. The main template that and you can make your own templates in AutoCAD if you want to, and if you get, we won't get that far in this class, but that's something you can figure out on your own if you want to. But the main one we'll work with is this AutoCAD.dwt. That's just a generic 2-dimensional AutoCAD template. We're not going to do 3D in this class. We're just sticking to 2D. In fact, when you get out there in the big wide world and you can't get AutoCAD for free anymore, it's going to be a heck of a lot cheaper for you to get the AutoCAD LT rather than the full-blown AutoCAD, because the main difference is that AutoCAD LT doesn't have the 3D features. Okay, LT is just 2D drawing exclusively, which is really more than sufficient for most of what we do. It's very rarely do we venture into the 3D world for our kind of drawing. So, when you get to that stage of your life and you feel like you want to have AutoCAD on your computer and you can't get it for free anymore because you're not a student, take a look at LT, because it's significantly less expensive. And we'll do everything, you can do everything in LT that we're going to do in this class, I think. So that's the 2D drawing. Now, you can, of course, open other files or whatever, but if you're starting new, you might just do that. So with AutoCAD.dwt selected, you can click Open, and you should be able to get a blank file at that point. There we go. So this should be, you should all see something very similar to this. Yeah? Yeah. So the other thing I want to make sure that you do for now anyway, until we get a little bit further, is if you've already, how many of you have already played around with AutoCAD some? Okay. Do you already have like preferences put into your AutoCAD 360 account?
Into the account? No.
So this thing up in the right, this sign in, the main thing that does is it syncs your preferences. So when you log into another computer or launch AutoCAD on another computer and you sign in, it will pull up all of your interface settings. So you don't have to redo that every time, which is super useful. However, that may get in your way. Again, we want to make sure that we're all working with the same interface for this class. So if you've got already a bunch of custom settings in your AutoCAD account, and I'm going to start making you turn all those off, and you don't want to lose all that work, you may want to log out of your AutoCAD 360 account, just so that the stuff I tell you to do doesn't like blow up all your settings in your account. Okay, so if you've already done that, you may just want to log out. If you haven't done that yet, if you have not set up any preferences in AutoCAD yet, then that's fine. Stay signed in, and as we kind of go through the class and start turning things on and enabling features, that all will start syncing, and then when you go to other machines, that'll all be there. Okay, because by the end of the class, you will have kind of you'll have customized your AutoCAD experience to something that makes sense to you, but we're not there yet. Okay, so everyone have something that looks like this on your screen? Anybody seeing anything vastly different from what I've got up here? No. Okay. So if you go, if you log on to the Canvas page for this class, there should be a couple of files on there. If you go to the Canvas site and pull up modules for this class, you should see 2 files. One is a PDF file, and the other is a .dwg file. I will attempt to demonstrate. So uncsa.instructure.com. Put in your info. Let's see. This is our class. And you go to modules. And you'll see something maybe like this. Actually, yours will look like this. Okay, and you go to modules. And I'm going to do my best to like post files on here that I want you guys to mess with. So here are the two files I'm going to play with today, or have you guys play with today. So go ahead and download both those. Yeah. Well, let's get you on. Should be your school. You went to uncsa.instructure.com, right? So it should be your email address for your student account. So you may need to like do a password reset. It'll send you an email. Instructure. 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 There you go. Hey, you're in. So type your email address, and then I have no idea what your default passwords are, but just click that Activate Reset Password button, and it'll set you up.
Turns out on my old version of AutoCAD, like the 2018, it never popped up anything, never watermarked anything.
Yeah.
With the 2019 that I downloaded like a few days
Yeah.
today.
Oh, nice.
Now telling me it's gonna watermark stuff.
Yay. All right, how are we doing? Did you guys, those of you that got in, were you able to download those files? So yeah, the first one we're going to work with is the DWG, that L is big chance system diagram v1.dwg. That's an AutoCAD drawing. So if you can download that, go ahead and open that up in AutoCAD, and we're gonna use that just to learn how to navigate around. This is just a simple drawing I did for a show a couple years ago. Oh yeah, there we go. Yay! Oh wow, you guys have so few boxes in yours. I'm jealous. Well, again, I've got like 50 courses on there, and I can't ever find. Okay, so on the left you'll see modules. Scroll up. Modules. And yeah, those are the files you want.
Is this a read-only file? Because
when you download it, probably is, but that's fine. You can, you can. I don't care if you want to blow this file up, but you can open it read-only, and then you'll just save it as something else if you wanted to use it.
Because if I open it, it opens 2018, which I
Oh.
have not uninstalled yet.
Oh, well, you got to force it to do 2019.
Yeah.
So if you go back to 2019 and just open it directly from there, then.
Okay.
So let me show you how that is done. Maybe you've already done the template here and you're up at drawing one. You can go to the file and just open, and then you can go find that drawing, which I think I've got it downloaded already. Oh, maybe I don't. Hang on. Let me go get it too. Download. There we go. Okay, so if I go and try to open it, I can now get it in my downloads folder. There it is. And now I have it too. And if it gives you this thing about unsupported objects, just hit Show Objects when available. It was created in a previous version, and there were some files tagged onto it that somehow are gone now. But Okay, so you should see, everybody got something like this yet? Yeah? Got the file open? Don't mess around with it too much yet, but. So in a minute, we'll talk about what all this stuff means. But for now, I just want to get around AutoCAD. So I think the first thing you really need to know, there's a few things you really need to know about AutoCAD. First of all, everything in AutoCAD is relative. Relative to something. So whenever you draw anything or do anything in AutoCAD, it's gonna reference some known location. Because AutoCAD works in sort of an XY coordinate thing. It's kind of like you're graphing, doing line graphs. You remember that from math classes in school. That's essentially what AutoCAD is. It's a really, really, expanded version of line graphs. Okay, so you've got an XY coordinate system, and you can kind of see that over here on the bottom left. You see where you've got this little arrow thingy. We call this the UCS, which stands for Universal Coordinate System, I think. Unified Coordinate System? I'm not sure. And you've got a little line pointing up for Y, and a little line pointing over to the right for X. So there is some location somewhere in this drawing that is what we would call the origin, or 0, 0. 0x, 0y. That isn't necessarily right here on the bottom left of your screen, although it might be. This is really just here to remind you which direction your drawing is pointing right now. But all of these lines and things that are positioned in here were all positioned relative to that location. Okay? So that's super important to remember, because everything you do in AutoCAD is going to be relative to whatever that spot was, or relative to some other spot that already exists that was relative to the origin. So it's possible to take, if you draw like an object, and then you want to draw another one, you can draw it relative to the position of the thing you drew before, but that thing you drew before was already relative to the origin, 0, 0. Okay? And so every drawing you do, you have to decide, where is my origin? Where is 0, 0 for this particular drawing? If it's like a theatrical drawing of like a ground plan or a section, there's a very specific place where that origin needs to be. And we'll talk about that in a few weeks. But for purposes of like schematic diagrams like this, it doesn't really matter where the origin is, but it just has to be somewhere. Okay? And then everything you draw has to be relative to that. Okay? We'll talk more about that and how to utilize that next week. So that's an important concept to understand. The next important concept to understand about AutoCAD is when you draw in AutoCAD, you draw in full scale. And what I mean by that is that, obviously if you're going to draw a ground plan of a theater, and that's going to end up on a piece of paper, the drawing of that theater if you have to scale it down in order to fit it on the piece of paper. If it was full scale, like as big as real life, then the piece of paper would need to be as big as the theater is in order to put the drawing on it. You know what I mean? So imagine like taping out the ground plan on the floor when you're doing a rehearsal room. Like you have to have a floor as big as the stage of the theater. Okay? So while the output of AutoCAD is usually scaled, right? It's scaled down. You shrink it down to fit it onto some arbitrary, or sometimes not arbitrary, piece of paper or PDF file or something. When you draw it, though, you aren't drawing it in scale. You are drawing it at full size. Okay? In other words, if the thing is 10 feet in real life, you are going to draw a line that is 10 feet long in AutoCAD. Okay? You're not going to draw a line that is, what if it's 1/4 inch scale? How many inches are you going to have to draw to get a 10-foot line? It'd be like 2.5 inches, right? So 2.5. You're not going to draw a 2.5 inch line right?
The other direction, that you were drawing a 10-foot line out of quarter inches, which is a lot of inches.
Well, what I mean by that is like a quarter inch equals 1 foot,
Yeah,
right?
so that's
Yeah.
a smart.
So you'd be drawing a 2.5 inch line, you know, if you were drawing in scale, right? But you don't. That's not how you draw in AutoCAD. You draw in full scale, so you don't have to do any of that mental math to kind of figure out. There are other CAD programs where you do, where before you draw anything, you have to specify the scale in which you're drawing this thing. You don't have to do that in AutoCAD. AutoCAD is you draw everything in full scale. So if you have a cable that has to run 100 feet, you're going to draw a 100-foot line in AutoCAD, okay? And AutoCAD doesn't care. It doesn't care how long the line is, because all it's doing is storing 2 points, right? The beginning of the line and the end of the line. So it's not actually storing a picture of a 100-foot cable. It's just storing 2 sets of coordinates. It's just saying, okay, there is a line, and that line begins at 1, 2, and it ends at 101, 2. Okay? And then when you open that, so when you save that file, all that gets saved are those 2 coordinates, which is why the AutoCAD file is usually very small. It's like kilobytes, very small file, because it's not actually storing a picture. It's just storing a set of instructions. So every time you open that file, it's redrawing everything for you on the fly. It's just following the sequence of commands that you did when you drew it originally, and it's just redrawing it every single time. It's called vector-based drawings. Okay, so it's not storing the actual picture. It's just storing the instructions that are required to draw the picture. Okay, and the instructions are much less data than the picture itself. Okay, so that's important. You're drawing it in full scale. However, you have to decide what units you are going to use, because AutoCAD fundamentally is unitless. Right? There's this arbitrary thing called a unit, okay? And a unit is, you know, if you're at 0, 0 at the origin, you are at 0 units x by 0 units y. And if you move to 1, 1, you are 1 unit over to the right and 1 unit up. And that unit can be anything. And in like a schematic drawing like this, it doesn't really matter what it is, what that unit is. But in a drawing of something that's in real life, like a theater or something, then that unit is very important, right? Does that 1 unit equal an inch? Or does that 1 unit equal a foot? Or does that 1 unit equal a meter? Or does it equal a millimeter? Or does 1 unit equal a mile? I don't know, right? But you got to decide what units you're going to do. So if you're, like I say, in a drawing like this, it doesn't really matter. But let's look at what the options are. AutoCAD has been around for longer than you guys have been alive, almost as long as I've been alive. But when it first became a thing, graphical user interfaces didn't exist when AutoCAD first, manifested itself into the universe. The mouse was not a thing. All that existed was you had a screen and a keyboard, okay? And so you had to draw everything by just typing. You would just type, and as you type, things would start drawing. So then over the years, they've just slowly, as technologies have matured, graphical user interfaces started coming up, mice started coming up. Even before like the graphical user interface for operating systems existed, AutoCAD had these really cool kind of tablets you could buy that had a mouse, but that synced to, but the little thing was like a virtual piece of paper that would sync to your screen in AutoCAD. So like they were kind of reverse engineering a graphical user interface that wasn't supported by the operating system of the computer. Of course, now the computer has all of that technology built into it. So that's all been kind of added on and built on as interface technologies have evolved, so has AutoCAD. But that fundamental technology of type to draw still exists. Like all that code is still there. And AutoCAD releases a new version every year because they have to have some reason to make you buy it again. Okay? And so every year they will change something just so that they can justify making you pay for it again. Okay? So every year there's a new version, and they will change one thing. And a lot of times the things they're changing didn't need to be changed. They were just fine already. But they got to change something in order to justify you paying them another $500 for your annual subscription or something. So the interface is this like constantly moving target. So I have found that the best way to keep up with it is to learn the part of it that never changes. And if I learn how to use it in that way, then all of that interface stuff can change, and I don't have to relearn anything. So that's a strategy that I found, and a lot of people that use AutoCAD have found works really well, because otherwise every year you got to like buy the book again. If like, okay, what's different, and how do I now use this program? So I have learned to use as much as possible that command line interface of AutoCAD. So without you, you don't have to do anything, but because the command prompt is inferred in AutoCAD. It's basically always waiting and assuming that you're going to type a command. Okay, so even though you can see down here at the bottom, it says type a command. That's what it's expecting you to do. It's not until you sort of interfere with your mouse that it decides to do something else. But by you just doing nothing at all, it's just waiting for you to start typing. So we're going to learn our first command. Are you ready? Our first command is start typing the word units. UN. And you see this little menu starts popping up? So if you type units and then hit enter, this little window pops up. Okay? This is where you set your units. Now, just for fun, go ahead and click cancel. And let's try it again. This time, just type UN. UN is the shortcut for units. So you don't have to type the whole word. You can just type UN, enter, and you'll get units as well. Okay? So there you go. There's your first AutoCAD command, units. Memorize it. Learn it. Okay? That should be one of the 10% that you remember of today. Okay? Let's look at our types here. So we've got our options are architectural, decimal, engineering, fractional, and scientific. The only one that's useful to me is decimal for a lot of reasons, but primarily it's because as you kind of progress through some of the things that we'll learn over the years in the program, you'll find that there's a lot of shortcuts that we use mathematically to help get us through a lot of the stuff we have to do in sound. And that math tends to be a lot easier to deal with if we're drawing and working and thinking in decimal units, particularly decimal feet. Right? So we tend to like to draw, if we're going to draw a 1 foot 6 inch line, we tend in sound world to prefer to just draw a 1.5 foot line. Okay? Because then later we have to do math on those values. Because if we have to figure out, okay, that 20-foot line, how loud will the sound be at the end of that 20-foot line as compared to where the speaker is 1 foot away? And doing that math is really easy. It's 20 dB, by the way. But trying to do that on some 18-foot 6 3/4 inch line, there's a lot of conversion traversals I have to do in my head before I get to the kind of number I can plug into a formula. Okay? So we tend to like to stick to decimal. Or engineering is also effectively a decimal thing, but generally decimal. However, technical directors and architects and people who like draw buildings, they like this architectural unit, which architectural units are 1 unit equals an inch. And you draw in inches, and so all of your values are like 1 foot dash 2 3/4 inches, which is like 3 times as many things to type, as opposed to just, 1.4 feet. Okay, so I prefer, for the most part, to stick with decimal feet when we're drawing, and by and large, most of the drawings that we'll do, that will be the easiest place for you to live in, again, because it lines up with a lot of the math we have to do. And so when we get into architectural drawings in a few weeks, I'm going to teach you how to scale those, because they're always going to come to you in these architectural units. And every time it comes, you're going to roll your eyes, and because I'm going to teach you how to do that. And you're like, stupid architectural inch units. I hate that. Why can't all the world think the way I think? Okay, but it's really easy. AutoCAD is quite happy to change that and scale that for you. I'll teach you how to do that later. But generally speaking, we're going to live in decimal. And then you've got various levels of precision. It's like how many zeros do you want after the dot? Again, generally speaking, very little of what we do needs to be precise, much past 3 decimal places. So I tend to go there, but AutoCAD, it's just a computer. It's quite happy to do whatever you tell it. It'll be as precise as you want it to be within the limits of the size of numbers that the CPU can store. And I think the highest you can go in decimal is 1, 2, 3, 4, 5, 6, 7, 8 decimal places, which that's an awful lot. I don't usually need to live in that level of precision. I'm not creating finely machined objects or anything. So, and sound is incredibly approximate. Pretty much everything about sound is approximate, and so close is good enough usually for sound. So I tend to stick to that 3 decimal places, and that's fine. And then this insertion scale, it's like this is like if you pull somebody else's object or drawing into your drawing, then should AutoCAD do anything to that based on, because it'll know kind of what units that was created in, and if yours are different, is it supposed to scale that differently? Essentially, this is where you say what 1 unit equals to you. Okay? So right now I'm saying, well, in my case, 1 unit equals an inch. But maybe you want 1 unit to equal a foot. Or maybe you want 1 unit to equal a micron.
I like light year.
Yeah, a light year. 1 unit equals a light year. A parsec. Sure, we'll do a parsecs. I'm going to draw in parsecs. Why not? Yeah, generally, in our case, it doesn't matter, right? So when you're drawing like a 1 line like this, it doesn't matter. But anything you want, doesn't matter. You can draw, yeah, hectometers. You can draw in hectometers if you want. Okay, doesn't matter because this drawing has no scale to it. There's no, it doesn't matter. But when you get to when you're drawing a theater, it kind of matters. Only because eventually you have to like put it in real life, and it's nice to be able to measure it in AutoCAD and then know that okay, that's 30 feet up in the air, right?
You don't think people understand 30 parsecs?
Yeah, everyone's got that shortcut conversion in their calculator ready to go, right? Right. Try that next time with your TD when you're ready to hang a certain cluster. And so, well, how high is it supposed to go? Just say,
Quarter of a parsec.
yeah, 0.78 parsecs.
You guys can do it. Just do the math.
And they're going to look at you. It's like, what? I told you. Like,
You're gonna be like, I have a computer in my pocket.
right? It's like, so usually you're going to be in our universe, you're going to be either in feet or inches. Usually feet in our case. And the reason for that, when you take sound system design with me next year, you'll learn more about this. But basically, it's because sound travels 1 foot per millisecond on average. And that's a really handy shortcut for us. So that's why we tend to draw in feet, because a millisecond is kind of like that smallest unit of time that we tend to like to deal with sound-wise, because sound moves relatively slow. So a millisecond is kind of our standard of how we like deal with time and sound. So 1 foot per millisecond, we draw in feet. That means if I draw a 100-foot line, I know it'll take 100 milliseconds for sound to travel that line, right? And that's a nice thing to not have to do that math in my head. Okay. All right, so feet, or whatever, it doesn't matter. There you go. You learned your first command, units. Yes. Okay, the next thing is let's just turn off some stuff, okay? Okay, so down here at the bottom right, these are sort of some what we call drawing aids. And I want you to turn a bunch of them off. Okay, so this one that looks like the Pac-Man vomiting something, I'm not sure. If you hover over that, it's called polar tracking. Let's go ahead and turn that off. Just click on that. Then there's this one next to it. It's called dynamic input. Let's go ahead and turn that off for now. This one's called show hide transparency. Let's go ahead and turn that off for now. Group selection. Let's go ahead and turn that off. This one called object snap tracking. Let's turn that off. Object snap, we're going to turn that off. We're going to turn these all back on later, but I just want to, I want turning them on to be a purposeful event, right? I want us to know why we're turning that on when we turn it on, not just say, oh, I'm sure that's useful. I'm just going to use it before you really understand it. So that's annotation visibility. We can leave that on. That's fine. You can leave that one on. Okay. And you can leave on this first one, which is grid display. You can go ahead and leave that on. That's not a big deal. If you turn it off, you'll see what happens is your background just goes solid. Yeah. Yeah, the dot is snap to grid, which again we don't need to do. Okay. So once you've done that, now we're all on the same page, right? We're all working with the same tool set now. All right, so how do I navigate around this thing? Well, let's go back to before such things existed, like trackpads and mice and stuff like that. How might we do that? What might be? Can you think of what command we might want to give AutoCAD? So if I wanted to get a closer look at a particular object on this thing, what? Zoom. Yeah, there you go. So type the word zoom. Zoom, enter. Okay, and notice that you get at the bottom some options. You can say all, center, dynamic, extents, previous, scale, window, object. So if you just type E for extents and then hit enter, what will happen is it'll just zoom to fit all the drawing into whatever your window is. Okay? So if you get yourself lost somewhere in your own drawing, I have no idea where I am, just do zoom extent. So for example, if you're, let's say you're way over here like this, and you're like, whoa, where did my drawing go? Because you zoomed really far out, and you're moving around I don't know where it went. Just type zoom, or just Z. Z is the shortcut for zoom. So just type Z, and then E. And by the way, spacebar and enter are functionally the same thing in AutoCAD. Okay? And it'll go, whoa, there's your drawing. Okay? Let's try it again. Let's type Z, enter. And then now go ahead and use your mouse, and let's just let's go take a closer look at this little section over here. So just do a click and then drag down and to the right to draw this box. Draw a box around this part of the drawing, and then click again, and it'll zoom to that part. Okay? Did that work? And then you can type zoom, Z, enter E to go back to the full size. Right? Everybody with me so far? If you have a mouse with you, you might also find that if you wiggle your scroll wheel, that will zoom. Okay? And it'll basically zoom to wherever your cursor is. So it's like if I want to go take a closer look at that same spot, I can just put my little cursor over that spot and then do my scroll wheel, and it'll go there. If you've got a trackpad, you can do kind of the pinch zoom thing, but that's like really awkward in AutoCAD because the scale of it never seems to be exactly what you thought it would be. Yeah, that's a fairly new feature that they added with the Mac version, is this sort of pinch zooming thing with your trackpad. And it just never seems to quite do the thing that I was expecting it to do. It's like, oh, that's not exactly where I want it to be, or that's not quite as far as I thought it was going to go, or that's further than I wanted it to go. It's a little awkward and takes a lot of practice, I imagine. I've never invested the energy to try to really master the precision of that particular tool. Yeah, so
I have 100% reliability.
so that's again, I would strongly advise you to just go with the mouse because that's going to be a lot more consistent. All right, so do a zoom extents again. And then, yeah, if you have a mouse again, if you remember that button 3. So if you click that button 3 and hold it, it does this sort of pan thing where you can kind of move the drawing around. And you're not actually moving the drawing, you're just moving your window that views the drawing, okay? So, you know, if you're zoomed in really far like this and you're like, I need to go up to the, you can just kind of pan and drag all the way up to the top of the list. And sometimes that's helpful, but eventually as you're like panning and panning and panning, and you go, where am I? Just again, zoom extents, and you can then see where you are again. How we doing? Everybody with me still? I haven't lost anybody? So far these commands are working? Yes? Okay. All right. So let's take a look at selecting. How do you select things in AutoCAD? So let's zoom in. Zoom in again down to this bottom area here, sort of like this. Selecting is one thing that I do use the mouse for pretty consistently. I mean, you can do it with the command line, but it's a little clunky because you have to know where all the coordinates are of everything, and sometimes you don't always know. So if you want to select something, you basically are going to just go over here, maybe sort of this blank area to the right, and just click your mouse. You just click and release, and you'll open up this selection thing. Now, notice if I drag to the right, I get this blue thing. You see that? But if I drag to the left, I get kind of a green thing, right? So, and notice also that when I drag to the right, it's a solid outline, right? That blue box is outlined with a solid line. But if I drag to the left, it's outlined with a dashed or dotted line. Okay? This is super important because depending on what you want to select, the direction in which you select it makes a difference. So if you drag to the right, so let's say I want to select this little drum machine object. If I click up here and then drag to the right, I need to fully enclose, whatever is fully enclosed inside of this box that I've dragged, that's what will be selected. Okay, and in fact, you can see now, this is again one of the newer features, they're actually kind of like making the parts glow a little bit that are part of the selection. But notice that it's not selecting the two connecting lines, the two purple connection lines, because those are not completely enclosed in my selection box. Okay, so if I do that and then click again, then it will have selected those things. Okay, now how do I deselect those things? Anybody know? I just hit escape.
Yeah.
Okay, just hit escape and it'll click around. So let's try it the other way now. So now I'm going to start my selection at the bottom right of this drum pad thing and drag up and to the left. And notice how you get now the green box with the dotted line. What this means is any object where part of it is contained inside of your selection box, if any part of it is inside your box, then the whole object will be part of your selection. So notice now that these two lines, which weren't selected last time, but they are now because I drug left instead. So now if I click, I'll get those lines too as part of my selection. So mastering the difference between that is going to really make your life a lot easier with AutoCAD, is understanding, okay, when do I drag right and when do I drag left? It depends, okay? And by the way, the answer to almost every question I ever ask in a class is either comb filtering or it depends, okay? So it depends, right? Every scenario will be slightly different, but knowing the difference will really make or break you in AutoCAD in a lot of cases. Is, okay, am I dragging left or am I dragging right in order to get the thing that I want? Okay. So just practice that for a little bit. Move around this drawing and try to select different things, and just kind of try to get a sense of how that selection box works. Try to, target a piece of it and say, I want to select that bit of it, and see what you have to do to get it. Okay, just do it. Practice. This class is about doing. So for example, try to select only that input label on this little box. So if I zoom into this headphone amp, what do you suppose the best way would be to select this input label? Yeah, you could click it, but using the thing I taught you to do, blue box would probably be the best way, right? Because you'd have to be really precise doing the green box to get only that label, right? It'd be really tough to get just that. But doing the blue box, it's relatively easy, right? I don't have to try all that hard. I can be really imprecise and still get only that input thing. And these are relatively simple drawings, but you might have very complicated drawings, so that if you get in the habit of just like clicking on the thing you want, and that's the only way you know how to select things, then when you get into a really complicated drawing, there might be 300 things, in proximity of where you're clicking, right? And so being able to really zero in on the bit that you're looking for using these window selections is really, really important and really, really helpful. If I wanted to get these two input, the input and the 1 and 2 and the lines that go to it, might be easier to do that by just clicking to, doing the green box. And notice that I got one thing extra with that, which was the left line. So you can kind of, if you hold down your Shift key and reselect that line, then it'll get rid of it as part in your selection. Okay? Make sense? All right. So go ahead and zoom back to extents again. Get back to your drawing. And let me think if there's anything else that I wanted to show you about that. I don't think there is. But what I would encourage you to do, there's no specific homework assignment for this week, but because I haven't really taught you a whole lot yet. But
I know how to zoom.
but you know how to zoom.
Homework assignment is to zoom.
You know how to you know how to do units, and you know how to select, right? So if anything, practice that stuff a little bit and try it with different input devices, right? So try it with your trackpad, get a mouse, try it with that, and just try to calibrate that before next week so that you've got a system, okay? Because this ability to navigate the drawing, to just look at the part you want to look at and not the part you don't want to look at, and select the part you want to deal with and the part you don't want to deal with, that's like fundamental make or break, your ability to use AutoCAD. Okay, it doesn't matter. Nothing else matters if you don't know how to like look at the part you want to look at. Okay, so and this is a simple drawing, but again, in complicated drawings, trying to figure out the part you want to look at can be really, really difficult. So let me show you an example of another drawing. This is one from like a whole show. Let's see. Okay, so if I zoom extents on this thing, I got a ton of stuff in here, right? So trying to figure out, okay, which part of this is what I'm looking for. Zooming extents is not going to really do it for you because there's essentially every drawing for the entire show is in this one AutoCAD file, okay? Which is that's not how I usually like to do it, but that's how this person did it. Because for this reason, because it makes navigating it, it's easy because then you only have to keep track of one file, I guess. But it's like trying to navigate that one file is really difficult. Yeah. Now there's a lot of ways that you can tame a drawing like this. You can use viewports and things like that and layouts and stuff to help you. But listen, I'm a busy guy, and I like to keep things simple because like I don't got time for that. So I would much rather just have 10 files in a single folder, and I know that each file I open only has one thing in it, right? Because it's just as easy to move that one folder as it is to move one file. Just as easy, right? Same thing. But it's not the same thing at all to open one file that has 20 things in it and try to figure out where's the part of it that I want, okay? That's really challenging. So like try to find the power diagram in this, you know? Gosh, I don't know. It's probably, it might be, no, it's not that. Is it that? No. Let's see. There's like 20 different versions of the system diagram on this thing. Oh, this looks like maybe power diagrams. Oh, hey, yeah. There's part of it. But look at this. Like, there's like a little miniature drawing of the entire theater in here that you can zoom all the way in on, right? Yeah, I don't know. Let me see. Yeah, I don't know. Yeah, I can't tell. Yeah, I don't know. Doesn't matter, but okay. So that's just an example of a much more complicated drawing. I mean, you guys are sort of like laughing at me because I'm like, hey, practice zooming and panning and selecting, and it's like, okay, but with one of these, like that's like really like practice, practice figuring out how to like find something. Like, you know, pretend that this little drawing I gave you is just as complicated as that one. Like, look, spot something on that drawing that is small and say, how do I get a closer look at that, right? So just master that skill this week, because you'll need to be a master of that in order to get anything else done. Which is why I'm not really going to teach you anything else about AutoCAD today, but that is just practice that part today and this week so that you can, like, that part's down. Like, you know how to look at files, zoom in, look at them, and pan them, and move around, and get to different places, because that's going to make or break you. All right, any questions about that? So you all have AutoCAD. It appears to be running. You know how to open a file. You know how to zoom. You know how to select. You know how to pan. You know how to, like, look around. So we're in good shape. So now what I want to do is take you through a couple of examples here. So one of the files I have on the canvas is this PDF file, I think, sound guidelines. So you can open this if you'd like. This is a document that
That was really fun.
yeah, that was. So back in 2007, I was a group, part of a 3-person group that created this document for USIDT, which was, until then, there really was no even closely resembling official guidelines or best practices for doing theatrical drawings for sound. It was just a free-for-all. Everyone was sort of like making up their own way. And so we created this document, which was kind of a recommended practice or guidelines for at least doing the schematics, the system diagrams. And we're still working on the rest of it. But I want to kind of take you through this. If you look at some of these things, you can kind of get a sense. And you've seen some of these drawings already just as a student here. You've probably seen some of these things. And this will be the first kind of drawing that we create in this class, is a system diagram like this. So when we create, remember I said that the system diagram is not a picture, right? And therefore a scale is not important, yes, right? Because it's not a picture of the thing. It's an abstraction of something. It's not a picture of a real thing. So it doesn't matter how long the line is. Well, I want to, like, take that idea a little bit further, which is that it's not a picture of anything. It's real, right? Your system diagram is not a picture of your sound system. A picture of your sound system would be a photograph of the equipment in the room, okay? And I've done that before. You know, sometimes if I've got a show that's got a lot of complicated analog settings on amps or processors or even mixing consoles, and I get it all dialed in and I got to leave, and then they got to run it for 2 months without me, sometimes I will literally take pictures of the rack or a picture of the mixer or whatever and just say, hey, if something's not working, just make all the knobs look like this picture. And then if it's still not working, let me know, right? So there is a place for pictures, but this is not a picture of a piece of equipment. This is a symbol or a diagrammatic representation of some kind of equipment. It could be anything, right? It's just a box that could represent anything. And that's when we're doing sound system diagrams, this is what we're doing, is it's an abstraction. It's a diagram of signal flow, or a diagram of the way things go together. And so this box is just a box. It's just a box. And you have little labels you can put on it to say this box represents something that exists in real life. But that thing could be a really small thing or it could be a really big thing in real life. But regardless of how large or small it is in real life, it's just a box that is of the same size in a drawing, okay? That's very, very important, because I see a lot of people get really sucked down that rabbit hole of making pictures as opposed to making diagrams. And if you think you're making a picture, then you're going to waste a whole lot of time trying to perfectly represent a picture of this thing. Like if this thing represented a mixing console and you were trying to make pictures, you've got to draw all the knobs and all the little buttons, and you got to get the, the radius of the, rounded corners just right, and, the colors of everything, and that's going to take you hours and hours and hours to draw something that looks like the thing, when that's not important for what you're trying to draw. What you're trying to draw is just how do things go together in this sound system, and how might signal flow through it. That's all you're trying to communicate. It doesn't matter whether it looks like the thing. We just have to kind of agree that we don't need it to look like the thing, that we are intelligent enough of beings that we can read a little label on something that says, hey, this little box is standing in for a thing called a Digico SD9. And we can say, okay, I know what a Digico SD9 is, and I know from memory what that looks like. It does not look like this box. But I'm going to suspend my disbelief for purposes of understanding this diagram, and I will accept that this box is an SD9, right? Because then I don't have to draw a perfect representation of an SD9, and you don't have to zoom and pan around inside of a very complicated perfect representation of an SD9, right? That's easier on you, and it's easier on me, okay? So we just accept that a box can be something, okay? And it can be anything that we decide we want it to be. And that will make all of our lives a heck of a lot easier. So, this box, you can just equipment type. This would be like, what type of thing is it? It's a mixing console, or it is a reverb processor, or it is a compressor, or it is a computer, or it is, a stage box, or it is a headphone amplifier, or whatever, whatever type of thing it is, you would just put that in there. Because like in my world, as someone who freelances as a sound designer and usually has other people that are sorting out the engineering details of that, I don't always know what equipment they have at the theater, but I can reasonably assume that they have things called mixing consoles and things called amplifiers and things called loudspeakers. I can assume that they have such things, even if I don't know exactly which specific things they have. So sometimes just saying the mixing console goes here, that's enough, right? Because then they will just use whatever mixing console they have and they will put it there in the signal flow. And I don't have to know exactly what it is. But if you do know exactly what it is, then you can write that across the top where it says make or model. So mixing console goes here, but then above the top says the specific mixing console I'm interested in, because like we have several in our shop. So if I was dealing with our shop, and I know they've got lots, then I would say, under equipment type, I would say mixing console. So mixing console goes here. And then over the top, I would specifically say, I would like the Yamaha LS9 16. Okay, and then they would know, okay, that's the one, and we'll put that one in there, okay? So don't make that mistake. Don't put make and model where equipment type should be, because the whole point here is to be abstract. You start by being very abstracting, and they get more and more and more specific as necessary. And then, so you make all these boxes that represent things, and then you just draw lines in between them to represent cables or wires or other ways in which they connect, okay? And there's a few little conventions that we set up, and these are the things we might revise, or we're working on revising right now, is that the conceit that we sort of set up here is that audio signal is going to connect left to right on things, whereas control wires or anything that's sort of like digital control, that'll connect out of the bottom of a box. And that helps you know the difference. So this line that's coming out of the bottom of this one, that's like a network control port. It allows me to control that mic preamp. But there's not necessarily any audio signal on that control line. Right? The audio signal is coming in and out of the left and right side. Okay? So that's just sort of a convention that we set up. Although since we created this now 12 years ago, that line between a digital control cable and an audio signal, it's gotten very, very, very blurry. I mean, you know, like, is Dante control or is Dante audio?
Both.
Yeah, the answer is it depends, right? It depends on what you're doing at any moment. You could use it to control something, and then a second later use it to send audio. It depends, right? So that's an issue we're wrestling with right now is, okay, in this new universe where it depends whether that cable is audio or control, how do we represent that diagrammatically? It's a little unclear. Yeah, we don't actually have the answer to that question yet, but we're working on it. We're trying to kind of figure that out. Is there, because ultimately, something that is a diagram, you shouldn't need to read a manual in order to understand a diagram, right? So we have to figure out a way to draw it that would make it really obvious to even someone who doesn't know all the conventions, right? They ought to be able to just, you ought to be able to look at a system diagram, having not known anything about this document, and get a general idea of what it's communicating, right? That would be an effective diagram. So that's an issue we're wrestling with right now. What is a very clear and easy way to represent a cable that could be either audio or it could be control in a diagram like this, but still allow you to infer or assume or know, otherwise know, which we're talking about, okay? We don't have the answer to that yet. The other thing that's important is you notice in this top right side where you've got this box and it has this little lightning bolt break line kind of thing on the bottom of it. Because this is not a picture of a sound system, and it is instead a diagram of signal flow, even though you might only have one mixing console in your sound system, for example, that doesn't mean the mixing console can only show up in one place on your drawing, right? Because your drawing is not a picture of the sound system. Your drawing is just a diagram of the way things go together, okay? And since it's not a picture, it's okay if things show up more than one place, right? If it makes the diagram easier to read. So if connecting something to your mixing console is going to require you to draw a line like this, to then connect to it, that is not going to make your drawing very easy to read, is it? Okay, if that's the path that you have to go through to get around all the objects that already exist, then that is not clarity, okay? And so it'd be, oops, I don't want to capture that. I don't want to get rid of that awful thing. Clear. It'd be much easier if you could just, make another box that represents that same thing and just say, that line goes there, rather than go all the way around, okay? And so if you're going to utilize that particular convention of, okay, things can show up in more than one place, you need to have some way of indicating that this thing, this box that represents this thing, does not represent a second one of these things in real life. It just represents another instance of the same single thing, okay? So if I draw a second box that is my mixing console, I'm not saying I need two mixing consoles. I'm just saying I'm drawing the same mixing console in a different place on the drawing than where it was before. And so that little break line, this little squiggly, is your indicator that this is another instance of the same thing that already exists. And you can even write underneath of that where the other thing exists. So where it says list other locations. So that other location could be on a whole other piece of paper even. So you could say, hey, this is another instance of the same thing. And to see the other instance of that thing, go here. And you'll see where that is, okay? But oftentimes, just that little break line is enough so that you don't think, so that you just know, oh, it's just a repeat of the same thing. You can also do, some people will do this little curvy line version of it. I prefer not to do that because in my mind, this represents to me that I I might not be showing the whole thing. Okay, that's what this infers to me, is that, oh, I just kind of chopped off. This is like tore off the bottom of this thing, and maybe I'll see the other half somewhere else. Okay, so that isn't specified here in any of this text, but that's just sort of how I kind of made sense out of the difference of those things. But generally, I prefer to just use the little squiggly to say this exists somewhere else. Okay. You can, if you want to, you can specify connectors on these lines, although I think that's probably more information than is required for a system diagram, because as we're going to learn in the class, we're going to create lots of different kinds of drawings. Okay, for clarity's sake, I would much rather have 2 drawings that have half the information each than one drawing that has all of it and is very difficult to read because there's so much stuff on that paper. You know, I would rather, you know, have lots of drawings that are individually easy to read than have one drawing that takes me forever to figure out what's going on because there's so much stuff in there. So if the system diagram is the only drawing you're going to create, and the connectors are important because, you know, you want to make sure that they use XLRs as opposed to 1/4 inches because they're better, then yeah, okay, maybe you might want to specify that. But you don't have to. You don't have to do that. Another option here is, again, this is a picture. This is not a picture. This is a diagram. So you don't necessarily have to draw one line for every cable. If you've got 10 cables that are all starting from the same place and ending up in the same place, you don't necessarily have to draw all 10 of those lines. Okay? You could do something like this where you just kind of fan them out and say, look, there's 24 here, and 1 is going to go to 9, and 24 is going to go to 32. And, you know, just about anybody can probably understand what that means, right? You know, does that make sense? So that's allowed. You can do that. I would advise to do that sparingly. Do it only if necessary. So if it helps make the drawing easier to read, then do it. If you're just doing it to save yourself time, then maybe don't do it. Because this does require a slight intellectual leap for the reader of the diagram, right? And that's okay, because most people ought to be able to do that. But again, in a very complex drawing, if you've got a lot of those kind of things, if you're requiring the person reading the drawing to make, you know, 50 of those intellectual leaps on a single drawing, you could run into some clarity issues there. But if it's a very complex drawing and it's got a ton of lines on it, and it's like, you know what, this would be a lot easier to read if this particular part of it could be kind of condensed a little bit, then that's when you would use this particular convention, if it makes it easier to read. But don't do it just because it makes it easier on you to draw, right? Because the whole point of doing the drawing is so that someone else can read it. You don't need to do the drawing for yourself because it's all in your head, right? Because you came up with this. So if you were the only one that needed to deal with this, then why would you do a drawing? You do a drawing so that someone else can make sense of what you're doing. That's why you do drawings for me. I make you do far more drawings than you probably will ever do out in the big wide world, because no one will ever pay you that many hours to do that many drawings. So you're probably not going to do a lot of these drawings that I'm going to make you do. But I make you do them so that it allows me to peer inside of your brain. The drawing allows me to see that you have thought about all the things that I want to make sure you've thought about. Okay, because I can't peer inside of your brain and see what's in there. I don't know how to do that. I imagine there are people out there in the world who know how to do that, but I don't know how to do that. But I do know how to read a drawing. So I'm going to make you create a drawing for everything that I want to make sure you have thought about. Okay? So you're drawing this for me or for the person on your crew that is going to walk in knowing nothing about this project. And they have to look at your drawing and know what they're supposed to do without having to spend 45 minutes of an explanation. So do these kind of shortcuts if it makes the drawing easier to read, not because it saves you time, because that's not the point. Patch bays. Patch bays are these little boxes full of connectors. So you tend to run into patch bays in theaters that have kind of installed sound systems. You know, if you're going into, you know, like 4-wall rentals in New York or something, you're not going to see a patch bay because you're going to run all the cable yourself. But in some of our theaters, there are patch bays because we've run wire through walls just to save us some time. And those individual wires may show up as connectors, individual connectors in little boxes scattered all around the room, but the other end of those wires all go to the same place, right? And that one place is usually a patch bay. It's usually a little box on the wall that has like 300 connectors in it. And those all go to little wires that then fan out and go to all places around the room. And so sometimes you want to be able to connect those together, right? Because on that big box of connectors, some of them would represent like connections on the wall, and the others might represent input cables that go to your mixing console. So you might want to take a little patch cable and connect that one that comes from the wall to that one that goes to your mixing console. And that way the mic that you plugged into the wall ultimately shows up plugged into your mixing console that way. So that's what this thing is doing. It's trying to show you patching. And so what would happen is, you know, each of these little, I call these carrots, these little, I call them Pac-Man things. All right. Those represent connectors. And so like the Pac-Man is eating the cable, right? So each of these represents a connector that's in the box of the patch bay. And then you're going to put a little patch cable in to connect those up together. Okay? And you would then put labels on it too. So next to this you would say, okay, this is, you know, labeled mic 1. There's a connector in that box that has the label mic 1 on it, okay? And then there's another connector that's labeled mix in 1. All right, and you're going to patch a cable between those two so that wall plate mic 1 shows up as mixer input 1 on the mixing console, okay? So that's what this is doing. And you know, you can do this HN and FN, that's full normal or half normal, or SN is shield normal, I believe, or sleeve normal. Not particularly important in our universe, but some people that becomes a factor for you. The other thing I want you to notice is you see how they've done the fan outs on this? And you see how the one on the left has a curvy line fan out? Right? And the one on the right has a right angle line fan out. What's the difference? Remember, this is a diagram, so everything represents something. Has anyone read the text to say what that means? So the mic patch bay diagram shown above, the input side are shown with curved corners, and the output side is shown in sharp corners. The difference indicates that the input cable is a multi-signal cable, and the output cables are a group of individual cables. So what that means is when you see a curvy line fan out, that means this is like a snake that has lots of cables that are all kind of wrapped together in the same kind of, you know, jacket. You pick up one cable, but it has like 10 connectors spilling out of it. Okay, let's call that a snake. But when you see it fanned out in the drawing with a right angle, that means these are all individual cables, but I am collapsing them for diagrammatic purposes. Whereas fan out with curvy lines means not only am I fanning this out for diagrammatic purposes, but it is also fanned out in real life. In real life, this is a bunch of connectors that collapse into one thing. All right? And that's an important distinction. So that's how you would communicate one or the other. So when I see a curvy line on a fan out like that, I'm going to say, oh, what snake are you using? Because the curvy line looks prettier, and so you might want to do that just because it looks cooler, but it actually communicates something. And that may not be the thing you want to communicate. Yeah, right.
You have like something in this drum that isn't really, or the standards don't really go over that input is like a Whirlwind W1 mass disconnect connector.
Right.
Like, so you have a cable that's maybe a fan to W1 that
Yeah.
goes into from your mixing console to the patch bay.
Yeah.
Then you have maybe a 1/4 inch patch bay or a military patch
Right.
bay, patching it into the amps or whatever, or to the processor. How do you document that?
Yeah. So if you're not familiar with what he's talking about, it's like some snakes. On one end is like the the spill of connectors coming out of it, and on the other end is like this one single connector that has 100 pins inside of it. Okay, and you might plug that into the wall. Okay, because there's another connector on the wall that has 100 pins on it. And you put those that way you're not plugging in 100 things on one end, and then all those wires that are inside that 100 pins on the connector then go through the wall and maybe show up on a patch bay or something. So how do you diagram that? And the answer is you don't, because in reality that interconnection of that multi-pin connector is not meaningful for the purposes of signal flow. Right? It's enough to infer that is going to happen. And that particular bit of detail is something I would put on a patch plot, which is where we would create a spreadsheet of going connector to connector through the system. Here are all the connector points, and that interconnection of that multi-pin it becomes important in that drawing. It's very difficult to kind of represent that in a flow diagram. Okay, we do have in here, if we somewhere in here, if I go, you have this here, which was kind of our attempt at talking about the thing you're talking about. But the problem is we don't really talk about like how that would be used or why that would be used. But you can kind of infer it here. So this is maybe like a patch panel on a wall, and you could put a connector there, and then you could have a molt fan, fans out like this that goes into that. So you could do it that way if you wanted to, if that was important to you. But I would argue, again, in the same way I would say it's not really necessary to label what your connectors are, because you're going to do that in a different drawing. I would say, that multi-pin thing is not particularly meaningful for the purposes of signal flow. For the purposes of signal flow, you just need to know that this wire goes to this thing, and the other end of it goes to this other thing. And what happens in between there is not particularly meaningful for the purposes of signal flow. In real life, it will be very meaningful, right? Because you got to make sure that you've got all the right adapters and all the right connections and everything. And that's something that you'll sort out in the shop or sort out on your patch plot, but not particularly meaningful for this. So I usually don't waste a whole lot of time on that level of detail in a system diagram, just because it's like extra work that I have to do that doesn't really change what the drawing communicates. Because ultimately, whether I go through all that hoo-ha or whether I just draw a line, I said the same thing, which is this signal that starts here ends up over here. And that's the important part for this particular drawing. Okay. So over here you've got this little dashed box that goes around this particular object. Yeah, it doesn't show up over there, but you can see it over here. You could use that convention to, if there's a piece of equipment, I've seen people go really overboard with this, and they'll draw a little dashed box around every single thing in the diagram with a label of where it is. Because the idea is this allows you to say, this thing exists or will be found or should be placed in a very specific location in physical space. Okay? So, for example, this mic preamp needs to be put in the control booth. Okay? And I've seen people go way overboard with that, and they'll put a box around every little thing and put a note that says this one goes here, this one goes at the mixing console, this one goes, and I think that's a waste of time. So, because I think it's a safe assumption that the mixing console will be found at the mix position. And I think it's probably a safe assumption that the amplifier will be found in the amp rack. I think that's a safe bet, right? You don't need to draw a box around it to say that, okay? So usually I prefer to use this particular convention if something is going to show up in a place that you would not expect it. So for example, a mic preamp, you might expect that to be near the mixing console, which is where the mics go, okay? But maybe you're using a digital console that has a stage box that does not have preamps in it. And so you're going to use an external mic preamp and put it in that rack in the orchestra pit to preamplify all those mic signals before you put them into the stage box to send it up to the console. And in that case, the preamp is going to be in a place that you would not expect it. You would not expect to have to walk down to the pit to turn up the gain on a mic, right? You would expect to be able to do that at the mix position. But this is a real life. I've been in this situation before. This is why I'm using this example. It's like, but in that particular situation, if you did not have enough gain on that mic, you would have to walk down to the pit to turn that gain knob, unless it was a remotely controllable one, which sometimes you have. But the important thing to communicate for purposes of this drawing is this particular object is not going to be found or should not be placed where you might expect to place it or find it. So you definitely don't want them to put this at the mix position, because then you can't get it connected to the mics that you need to connect it to, okay? So you would use the box to indicate that. So I use the box to talk about unusual things or things that might change. For example, if there's something that only is going to be in your system during tech but will disappear as soon as the show opens, maybe you draw a box around that and just say tech only, right? Or tech table, right? This should be at the tech table when the tech table exists. But when the tech table does not exist, neither should this thing, right? You would use a box for that, okay? So you remember that time I said, hey, rather than draw a big, long spaghetti line all around to get to a thing, and instead just draw another instance of the thing? There's another way around that problem, which is that instead of drawing another instance of the thing, just don't draw the line all the way across, okay? So what's going on here is if I've got a really complicated line that would have to be drawn and maybe I don't have room to draw another instance of that same object, I can do this. I can draw the line and have it terminate with a little symbol like that with a number on it, and that number would have a twin. So then I would go up to the object where the other end of that line should be, and I would draw a similar box with the same number, and then have that line going into the box. And that gets you, that's a little way to get out of jail free card. If you kind of get into trouble with a diagram and you realize, oh crap, there's no way to get this line where it needs to be that isn't going to be a complete disaster. This is your get out of jail free card. This is another one to use very sparingly, because that's another one of those intellectual leaps that you've got to require of the person looking at your drawing. Okay, they've got to, if there's 30 of those in your drawing, it's going to take them a while to find the other end of each of those. Okay, but if there's only one or two of them, then okay, that's not going to be too tough. So use that sparingly. The other one is, let's say I already had a line that was going down that way, and I needed this line to go left to right across there. Well, you don't want the line to touch, because someone might infer that there's a splice going on there, that maybe that's wire touching wire rather than just line touching line in a diagram. So you want to be very careful about that. So one way around that is this little squiggly line. So you draw the line out here, and then you do a little squiggly, and then you do another squiggly there, and keep the line going. And that way, you just have this line that gets to still be there, and then this little thing, you're just saying, hey, that hopped over. Yeah?
So I know that you mentioned electronic schematics.
Yeah.
At a point where there's a splice, you just draw a circle around the thing, and
Yeah.
you can do whatever
Yeah.
sections you want.
Yeah. So,
Why was the choice for this?
well, we have that actually. So let me see if I can find it. Yeah. So here's an example of what you're talking about. So here I've got the mic preamp, and I've got a Y cable that goes into the CD recorder and the computer. So the CD recorder is like my backup recording device, but I'm really using the computer, and I want signals to go to both. So I've got, the lines are touching in a few different places here, but I'm using the dots, those little black dots, to indicate that this line touching this line, that's actually copper touching copper.
Yeah.
Whereas the line that's touching this other line that doesn't have the dot, that's just another line that's touching a line on a drawing. There's no actual intercourse happening, right, with those two lines in real life. And so that's one method of clarity. So, yes,
Yes.
right?
You also have the, so here it shows the two little squiggles. A lot of people also do the half circle going over one line.
Right. Yeah. So another option, which we didn't put in the spec, but is kind of something that a lot of people will do, just because it's anytime the problem I have with the little squiggly is, again, intellectual leap. And if you got too many of them, like maybe somebody will infer that the other end of that squiggly is different than what you thought it was. If you got a lot of little squigglies, how do they know which one goes to which one? Hopefully they're very close together and it's very clear, but sometimes it's not. So a lot of times what people will do is they'll just do this. It'll stop there, and then they'll go, whomp, and like that. And that's a way to be just like super clear that this line is just like hopping over this other line. It is not meant to infer any type of actual, wire touching wire. Okay. So yeah, in a perfect world for me, that's what I would do. Is I would do this, and then I would do this, right? And then I'm like absolutely totally clear, right? No ambiguity here, hopefully. Okay. So this is my preference, which is why you see a lot of people doing that around here, because you come here to do what I tell you to do, right? Not what you want to do. You can do what you want to do when you leave here, but you come here to give my opinion on things. And so my opinion is this is clearer than some of these other options. And you're allowed to disagree with me, but not until you leave here.
Another thing with the other, to specify the hex thing to go to another
Yeah.
section of the drawing. If you go to another plate, people just have, or I've seen this large hex that says C plate.
Yeah.
As opposed to, and there's no matching numbers, or
Right.
is that correct, or should it follow that?
Again, I would err on the side of clarity. What is the most clear? If it's on another plate, then I think that's a label thing, right? So you would do the little symbol, but then next to it you would write, okay, look, you're going to have to go to this plate and this area of the paper on that plate in order to find this thing's twin, right? So I would err on that just being overly specific, and that's okay, but you don't want to give anybody room to assume anything, right? You have to rely on assumptions a little bit, right? You're assuming that people understand that a box can represent anything, but you don't want to overly rely on assumptions. All right, let's see here. Talked about that. Okay, here's amplifiers. These are just different ways of diagramming an amplifier. Again, an amplifier, it's just a box that could represent anything, but we are using, there is kind of a convention in electrical schematic diagrams where this little triangle represents amplifier. So we went ahead and adopted that. So if your object is an amplifier, then you can draw the little triangles. Now, the reason the triangles are important is that amplifiers can have, something that is a real amplifier physical box in real life could have multiple amplifiers inside of it, right? So like that one over there in the rack, that has actually 2 amplifiers in it, even though it's 1 unit. You can put 2 separate signals through that thing to get amplified. And there are amplifiers there are 6-channel amplifiers, 8-channel amplifiers. Think about like home theater amplifiers, like home theater receivers. They've got, like mine has 11 amplifiers in it, okay? So that's why the triangles are important, is the triangles indicate how many actual amplifiers are inside of this box that's representing an object in real life, okay? So, and then there's various diagrams to show how those amplifiers might interact with one another, because sometimes they might work autonomously and sometimes they might not, right? You might say, well, I'm going to take the same signal and send it to both amplifiers in the box, and that would be a parallel mono. Or you might take the same signal and utilize the combined power of both amplifiers to feed a single thing, right? Because maybe the one amplifier itself isn't quite going to generate enough signal for you, and so you can couple the second amplifier with it, and they can do more work. And that would be a bridged amplifier. So that's this third one with that little diagram shows, hey, I've got one signal coming in, but then I'm combining the output of both of them to feed the same thing, and I can get twice the power that way. Although not necessarily twice the signal, as we'll learn, or twice the perceived signal, as we'll learn in system design class. Okay, so that's amplifiers. Notice this weird thing here where I've got two lines feeding into a single NO4 on a patch panel. That's just to say that in like a top sub configuration where maybe you've got a single amplifier driving the high frequency horn and a separate amplifier driving the low frequency driver. Ultimately, that's probably going to go into the loudspeaker on a single connector, like an NL4 that can have two signals on it. So notice we're doing right angle lines until we get to the part where it merges together, and we're doing curvy lines. And what does the curvy line represent? Yeah, it ultimately combines into a single physical thing in real life. Okay? So these two lines are not just showing up in the same place on the drawing, but they show up in the same physical place in real life. So you'll have two wires that actually come together into a single connector. It'll look like a Y cable, in other words. Okay? And so, you know, one leg of that Y will go into one amplifier, and the other leg of that Y will go to another amplifier. So that's what we're communicating there. And then you got loudspeakers. You know, again, we've just kind of come up with a generic drawing. We're not using the standard equipment block, mostly because by the time you get to the loudspeakers, you got a lot of them, and you've got more room to write out to the side than you do on the top, because usually you're stacking them, because signal flows left to right. So, and we again added a little symbol inside of there because a lot of times something that is a single box loudspeaker in real life might have more than one loudspeaker driver inside of it. And knowing how many drivers are in it can sometimes be important information, especially if you're doing something like this where you're bi-amping, right, where you've got 1 amp feeding the high and 1 amp feeding the low. Knowing that there's more than one driver inside of there is important information for purposes of signal flow. Okay? However, one of the things that I kind of usually ask you guys to do in your drawings is, even if you're not bi-amping like that, even if you're relying on the internal crossover and you're only feeding one signal into the loudspeaker, I still want you to draw how many drivers are in there so that I know that you know how that loudspeaker works. Right? You know, again, for purposes of signal flow, that's not super important, but it's another way of you letting me peer inside your brain, that you know that when you specify that loudspeaker, you're actually getting 3 loudspeakers. I need to make sure that you know that. Right. Right, exactly. And so I try to catch that stuff when I can, but because when I see that kind of stuff, I realize, okay, you don't fully understand what you're working with here. You don't fully understand what you're specifying. Because if you're specifying that thing that has 3 drivers in it and you're drawing it as though it has 1, there's a really important feature about that particular loudspeaker that I got to make sure you understand, which is that its directivity changes depending on which way you move it. You can move the horn inside, or you can move the box around the horn, and this directivity is going to widely change because of the way the drivers are in there. And you need to understand that before you try to hang it up in the air. Because once you put it up in the air, if it's not in the right configuration, it's not going to do the thing you think it's going to do. So I want to make sure that you know that. So that's why I'll usually have you draw all the drivers, even if you're not bi-amping or tri-amping or whatever. Okay, we've got, this is a symbol for a microphone. It's, you know, a little circle and the line. Okay, the line is the diaphragm of the microphone. Okay, so microphones are just backwards loudspeakers. Okay, most of them anyway. And so whereas a loudspeaker is like a big piece of paper that pushes and pulls on the air and makes the air molecules bounce off of each other, a microphone is the opposite. So there's a piece of paper or something like paper inside of that thing, and as the air molecules push and pull on the piece of paper, it moves it. Okay? And so that's called the diaphragm of the microphone. There's got to be some big object that catches that air pressure. Okay, so that's the thing, that, the line shows where the sound comes in. The sound comes in against that perpendicular line. And then the circle just represents the rest of the microphone. Okay, the magnet, the housing, the whatever. Okay. And then you've got a signal line coming off of that. But what you don't want to do is draw it like this, because that's not how it works. Okay? And if you draw it like that, then you're going to get a 30-minute lecture and lesson from me on how microphones work. So if you don't want to get that, then draw it correctly, because if you draw it the second way, then I'm going to think that maybe you don't know how microphones work. And the teacher in me is going to say, ooh, here's somebody who doesn't understand something. I'm going to teach them. And maybe you actually do understand that, but your diagram just indicates otherwise. So, and then you get a 30-minute lecture you didn't need. Okay? So draw it correctly, and then I won't assume that you don't know what it means. Okay. This is just an example of how you might combine some of these conventions to demonstrate something, like a wireless mic. So the wireless mic, like I'm wearing right now, it is ultimately just a microphone. There's a part of this that is just a microphone that has a little diaphragm that then transduces that air pressure into electrical signals. And so you can draw that just as a microphone. But that microphone plugs into a little box that is not a microphone. This little box is not the microphone. This is a transmitter. This is a wireless audio transmitter. So that's a piece of equipment. And diagrammatically, this little transmitter, this little teeny tiny thing that's not any bigger than a deck of cards, is no different from that mixing console over there on the bench. From a diagrammatic point of view, they are diagrammatically functionally the same. They're just a piece of equipment. So you draw them that way. So this gets that standard equipment block as a transmitter. So I've just got a microphone plugged into a transmitter, and transmitter is just a piece of equipment, even though it's small. Okay? And incidentally, if it's a handheld mic, it's the same thing. You still have a microphone that has wires going into a transmitter. It's just the transmitter is inside of a thing that looks like a microphone. But it is, diagrammatically, it is the same thing, because sometimes you can take the microphones off of the transmitter thing. You can unscrew them and put a different one on there. I don't know if you knew that, but it's possible to do. So I need to make sure that you understand that, so that because if you don't do that, then I'm going to think maybe you don't know how handheld wireless microphones work. And so you might get a 30-minute lecture from me of, hey, you realize that this is no different from this other thing, and you can actually take the diaphragm off of this thing and put a different one on. Did you know that? Because your diagram might suggest that you don't know that. And so if you don't want that lecture from me, then draw it like this, and then I'll know that you understand how that works. And then you've got a receiver, which, again, in this case is a larger thing than the transmitter in real life. But diagrammatically, they are the same size because they are functionally the same thing. I just label it differently. I've got a transmitter and I've got a receiver. And then there's magic fairy dust in between that lets the sound go. It's not a wire, right? So I'm not drawing a line between them because there's no connection. There's no physical connection in the visible world that we can see. There is some invisible things going on called electromagnetic waves that are carrying our signal. The electromagnetic fairies are taking our audio and carrying it through the air to the other thing. And so we use this little lightning bolt thing to indicate the magic fairy dust. And then underneath of that, you can say what particular brand of fairy dust you're using, which in this case is the frequency, right? But it could be something else. Maybe someday we'll learn how to do this in the quantum realm, and so you could say which quantum particles you're using, or I don't know. All right, so that's it. And then this last page is just like, hey, and yes, for the Noras of the world, we did not invent these ideas out of nowhere. So we kind of like took an existing convention of schematic electronic diagrams and kind of stole the same ideas and just created some of our own symbols. But we acknowledged that those symbols exist, those other symbols exist, and they would work inside of our conventions, right? So if in your purposes of your signal diagram, like maybe you're going to put a potentiometer, you're going to actually put a a passive volume control on a wall, which exists sometimes in dressing rooms, you could use that potentiometer symbol from electrical standards, and that would make sense inside of our standard, right? That would still work. So we're just acknowledging that yes, we know.
What Jake's got is the squigglies at the bottom of the box that are just resistors. Like
Yeah.
in my brain, I only ever see those as resistors.
Right. Yeah, but see, we're showing that, hey, look, this is how like our ideas fit into these other people's ideas, right? Like it
It's almost like they're related.
yeah, there is a way to make sense out of these seemingly disparate conventions, like they do connect in some way or can connect in some way if you need them to. Okay, so that's that. So by the way, what we're going to do next week, once I teach you how to draw a few things in AutoCAD, is I'm going to make you draw all these symbols. Okay, so that's the first project. I'm not going to make you draw a diagram. I'm just going to make you draw these symbols. You're not going to learn text for a couple of weeks. So independently of the text,
Text is advanced.
but that is. But for now, like next week, I'm going to teach you draw a box with a line. Can you do that? Can you draw a box with a line? Right. Minus the text. Just I want to see you do that. Can you draw a box with a line with a little squiggly at the bottom? Just little things like that. Like, can you draw can you draw a line with a circle next to it and a line coming out of it?
Yeah.
Right. That's the assignment for next week. I'll teach you how to draw some things next week, and I'll teach you how to draw circles. I'll teach you how to draw boxes. I'll teach you how to draw lines. And I just want you to take those three things, and you should be able to draw pretty much every symbol in this document using either a box or a circle or a line. Okay? No, we won't do those ones. Just Okay. So that'll be. So you have that to look forward to. Okay. All right. How we doing? I got 20 more minutes. Good. Yeah. I don't know who did, but somebody did. All right, so one more thing I want to take you through in our last few minutes is I keep referring to a lot of these other drawings that you might do. So for example, this is a system diagram that's a bit more complicated than the one that I showed you for my show. This is for a little bit larger show. So you should be able to kind of look at this and get more or less a sense of what's going on here. But this is an example of how you put all these things together. For example, just for purposes of saving space, she elected not to do the magic fairy dust lightning bolts in between the receiver. She's just inferring that, and I think that's probably reasonable. Because it's like, why am I wasting all this space drawing fairy dust lightning bolts? When I've got a ton of other things to draw on this drawing, right?
Everyone knows that sound doesn't work without the fairy dust.
Yeah. So, there you go. System diagram, right? But I want to talk about some of it, because we're going to learn how to do lots of other drawings. The first half of this semester is really going to be AutoCAD, doing system diagrams and a few other things. But the second half of the semester is going to be other stuff. So it's not just an AutoCAD class. So for example, here is what I refer to as a patch plot. And you got to zoom in on this thing to really understand what's going on. But a patch plot is a spreadsheet that this is where we get into the details of like all the connectorage that goes on in a system. So we've got a cell for every single connector that exists in this sound system, and a cell for every single wire and cable that is in this system, and a cell for every piece of equipment. So this is like high level of detail. And again, probably in the big wide world, when people are paying you for your time, probably not going to spend a whole lot of time doing this detailed of a drawing. Okay? But I am going to ask you to do this detailed of a drawing because I need to know that you have thought through all of this. I need to know that you know that you're going to need a TA3 female to XLR male cable in order to make this thing work. I need to know that you know that. so that I don't get a call at midnight on a Saturday during a tech because you realized that, oh crap, it's a special cable, and I didn't know that it was a special cable, and therefore I didn't get one. I need to know that you know that so that I can actually go to bed that night, as opposed to have to deal with your emergency. Okay? So we'll talk more about these later. That's a patch plot. Another patch plot. Another patch plot. Okay, this is kind of riffing on the concept of system diagram. This is a control diagram. So as opposed to diagramming audio signal, I did an entire diagram for the control. So that's one way around that ambiguity of, is it a signal or is it a control? Is it a whatever? Well, I'll just make a separate drawing. I'll make one drawing where all the lines represent audio signal, and I'll make a different drawing where all the lines represent control. Okay, so we're using all the same conventions for an audio signal flow diagram, and we're diagramming control. So this is how all the different things controlled. In this particular show, there was a sequence that had to be synced to timecode. And so the audio playback, and there were, it was three light boards, and there was a projection media server, and all, a bunch of amps, and they were all getting commands, from an automation system that was locked to a timecode signal. So that's what's going on here, is we're just kind of showing that was a very complicated little thing they were pulling off, and so so you got to diagram that, because that's going to be tricky to set up. So show me that you understand how this is going to work. So they made a diagram of how that works. Another patch plot. Oh, a patch plot for the control system, right? This is a loudspeaker plot in ground plan view. So this is a plan drawing of the theater. So you're looking down at the theater from heaven, and you see what it looks like from the top. And we're showing where the loudspeakers are. So we've got a little box that represents a loudspeaker, and we've got a label next to it that says, here's what that loudspeaker is. And you will find that exact label with exactly those words in other places in this document. Where are the other places I might find that? Yeah, so I will find that exact string of words in the system diagram. Sometimes we call that the one line. That same exact label will be next to a box representing that loudspeaker on the system diagram. And that exact set of words will also be on the patch plot on a cell that represents that thing. So it's very important that you're consistent there, so that, again, we can traverse all these different drawings and know that you're talking about the same thing. Okay? So a lot of times people will not do that, and then they'll get another half-hour lecture from me about that, because it's like, how am I supposed to know that this thing on here is the same thing as the thing over there when you're calling it something different in both places, right? That is not clear. And you got to pretend that I'm really stupid, because maybe I am, and maybe I will get the wrong idea. Okay, so but the important bit of this particular drawing is, where does the loudspeaker go? Like, where's it going to live and sit in real life? And where does it point? Those are the two important things here. So we've got, where does it live, which is right here, and where does it point? Right there. Well, X marks the spot. If you were to put a little laser pointer on that loudspeaker and turn it on, you should see a little dot showing up at that seat in the theater. Okay? That's the important information here. Where does it go? And where does it point? Same thing in section view. So now we sliced the theater in half, and we're looking at it from the side. And you can see where all those same things show up. Again, where do they go? Where do they point? And the reason we had to do this view is the ground plan doesn't show us where in vertical space does it live. So the section view shows us where in vertical space. So like that KF850 that was on the ground plan, you didn't know this from the ground plan, but it's actually sitting on the floor, as opposed to these other ones that were right next to it that are up in the air. And you wouldn't know that from the ground plan, because here's the 850 and there's the Q10, and they look as though they're on the same plane. You wouldn't know that this one's on the ground and this one's in the air. So that's why we have the section view, so we can say, oh, look, that one's on the ground, that one's in the air. And again, where does it go? Where does it point? Anybody notice a problem here yet? There's a discrepancy between our ground plan and our section. For the KF, look at the KF850. So look at the KF850 on this drawing. And now look at it on, oops. Now look at it on this drawing. What's the discrepancy? Huh? Okay, yes, but I could assume that the other one is behind it, right? That's not the discrepancy. There's conflicting data here. Okay, what did I say was the point of this drawing? Where does it go? And where does it point? So the where does it go makes sense. Like it's in the same spot here as it is there, but look at the where does it point? So this one says point there. This one says it's pointed at the front row. Which is it? Is it pointed at the front row? Is it pointed at the back row? Huge difference, right? Because if it's got to point at the back row, I got to take this thing that weighs 300 pounds and I got to figure out how to tip it up without falling over. So which is it? Which do I have to do? I don't know, because the drawing isn't clear. It's giving me two different plans here. Which plan are we going with? Are we going with the back row plan or are we going with the front row plan? I don't know. Doesn't say. That would get you a 30-minute lecture from me. This is sort of ease. In this case, we're using Lara plot directivity plots. We're not going to learn this in this class. This is a next year kind of thing. But basically, the different colors line up with loudness. So red is louder than green, and green is louder than blue, sort of thing. Just kind of shows you where the sound goes. Again, we'll learn more about that next year, so don't worry about it yet. Rigging diagrams. So if the loudspeaker plot is where does it go and where does it point, the rigging diagram is how does it get there? How am I going to get it to that spot and make sure it stays there? That's what the rigging diagram is. You don't want to put all that detail in the loudspeaker plot because it'd be too small to really understand it. So that's what these are rigging diagrams. This is like, okay, here's that Q10 that was up in the air. How does it get up in the air? Well, we're going to wrap a chain around an I-beam, and we're going to drop that down to a shackle that's going to connect to a little aircraft cable stinger that's going to connect to another shackle that's connect to a bracket that latches on to the top of the loudspeaker. And we've labeled all this stuff. That's a 3/8 inch Crosby 209 screw pin shackle. And it ought to be able to hold a 1/4 ton safely. And this thing weighs 49 pounds, which is a lot less than a 1/4 ton. So I think we're safe. Okay? So it's like, how does it get there and how does it stay there? Right? That's the important part about a rigging diagram. How does it get there and how does it stay there? Because getting it there is one thing. Making it stay there is another thing entirely. I mean, you may very well someday have to hang a loudspeaker array that is a 1/4 ton. How are you going to get it to stay there? Because things that weigh that much tend to not like to be up in the air. Okay? They tend to want to fall down because that's how gravity works. So, yeah, it's a lot harder, right? It's just a lot harder to do it. So you're certainly not, you're not going to get 10 people to stand up there in the catwalk holding this thing up because that would be expensive and maybe not safe. Here it is again. Here's another one. So again, tons of detail, tons of clarity. How does it get there? How does it stay there? This is a power diagram. And there are really two purposes of the power diagram. Well, three, I'll say. One is like where does it get its electricity from? Because audio, by definition, relies on electricity. So you understand the difference between sound and audio? Sound is air. Audio is sound in electrical format. Okay? So audio is sound that's been converted to electricity. Okay? Whereas sound is air molecules bouncing off each other. Okay? So these are both sound systems and audio systems. But sometimes we use the terms interchangeably. But audio equipment, audio by definition, involves electricity. So power diagram, first and foremost, is where does it get the electricity from? Because what audio devices do is they manipulate that electricity in a way that approximates a sound. Okay, so it has to have electricity to begin with before it can manipulate it. So where does it get that electricity from? That's the first thing we want to know. Yeah, that's where it comes from. Walls, right? That's where it comes from. It just lives in walls, right? No problem at all. It's just open up any wall you want. You'll find electricity in there.
It's like a maple syrup
Yep. Yeah. So not exactly, right? So, in fact, we as a human race, are kind of like wrestling with that. Like, where does our electricity come from, and where ought it to come from? Because are we getting it from the right places? Maybe not. Like, maybe the places we're getting it from aren't going to work, forever. So, are there other places we could get it from? I don't know. But either way, you got to diagram it. Where are you going to get it from? And yes, eventually you get it from a wall, because there comes a point where you don't have control over where it comes from, right? Okay, because eventually you have to involve a power company and a nuclear power plant or something, and you don't want to be in on that action. So, yes, eventually it's a wall, but you want to at least diagram the parts of it that you do have control over. So, like this thing at the top of the diagram, that is the last thing in a wall that you can touch, that you have any control over, and it's a 2,000 amp 3-phase box somewhere on a wall that has quite a lot of capacity for electricity in it, and that's going to feed all of the things on this drawing. And that thing, when it says breaker, there's a big lever on a wall that you can touch, or because it very well might decide, that lever might decide to move all by itself. Okay, and the reason it might move all by itself is if you're trying to pull too much energy through it, and it has like a fail-safe built into it. If you try to pull more energy through it than it can handle, then it'll start heating up. Right? That's what happens when you pull too much energy through something. It starts getting hot. And if it gets too hot, what does heat turn into? Fire! Right? And theaters and fire do not go together very well, okay? There have been many theaters that have fallen victim to fire, so we tend to really not like fire inside of theaters. And whenever we do have to have fire in theaters, like we have to have fire marshals standing there right next to the thing that's on fire, holding a fire extinguisher, watching it. And if it ever decides to get out of hand, it goes out immediately, because theaters and fires are really, really bad combinations, okay? So we do not like fires in theaters. And so all of these little boxes, when it says the word breaker, that means there's a switch or a lever or something that will, it basically will, it'll either blow up in a very controlled way. So there's a little wire contained in a perfectly sealed box that will just kind of blow up to stop that electricity from flowing, and it doesn't blow up in a way that catches something on fire. Or it's a little breaker box that will just, it's just kind of like it's like a bone that gets popped out of socket, right? It'll just kind of go, oh, not going to do that. Okay, and it'll just, like, that little lever will just go, and it'll stop all of the electricity, okay? And so if that happens, your show goes down, right? You don't have any sound anymore because you had to convert your sound to audio and then convert it back to sound. And so while it was in audio world, it vaporized and you don't have a show anymore. So you have to know that there was a thing on a wall somewhere that probably got dislocated. So you have to go and push it. So everything that's on here has a place. But you're also indicating how much energy can I put through that thing before it dislocates itself. So that's current. So when we say amps, when I say this is a 40 amp breaker, that means I can pull 40 amps through it before it dislocates itself. And so I want to make sure that I'm not ever doing that. So down here at the bottom, you're saying this amplifier, worst case scenario, 10 amps. That's the most it's ever going to pull. and then you kind of add that all up, and you say, all right, the total I'm pulling off of this 2,000 amp thing is 154 amps. Not too bad. I'm not going to be the one that trips that breaker. Now, there might be other things that are also pulling off of this, and hopefully they're not a whole lot more than I am. They might be, but it's certainly not going to be your fault if it breaks, okay?
On another diagram,
Yeah.
they had different triangles for the amplifier.
These are just like Ys.
Oh, no.
Oh, triangle. Yeah, just
Is that just by choice?
yeah, just to say, hey, that's an amp, just for fun. Okay, so more power diagrams, power diagrams, power diagrams. This is just a matrix patching. ClearCom plot, so where are the headsets? Where do they go? Where do they plug into? More headsets. Rack diagrams. Super important that this thing doesn't end up in that rack, because that rack is in a physically different spot in the theater than this rack. So you got to make sure that you say which things have to go in the same racks together, because the racks go in different places. So you just diagram it. It's pretty easy. In fact, I'm probably not even going to teach you how to do this, because it's super easy to do. Pit plot, where do the musicians go? Matrix routing for the console. More matrix routing for the console. Wireless plot, so who gets what element, what serial number, what frequency, where does it go, all that kind of stuff. Pretty easy to put together. It's just an Excel spreadsheet. Equipment list, this is all the equipment that you have to have in order to do this thing as diagrammed. So this would be all the things, this would be your rental sheet. There would be a price at the end of it in real life. This is all the stuff you need, and when you need it, and when you're going to bring it back. Timesheets, there are various ways of doing this. This is like, when do people work? Because in real life, you have to pay them for every hour that they work, or every block of 4 hours that they work if they're IA. So you have to, and in this case, I have you guys kind of predict what you think it's going to be, and then keep track of what it then is in real life, because ultimately you have to get really good at predicting that, right? You have to be able to say, this project is going to take this many person hours to do, okay? And each person hour costs me this much money. And so if it's going to cost me 100 person hours, and I have to pay people $20 for every person hour, then how many dollars do I need? No, that's a real question. $20 per person hour, and I need 100 person hours.
No, shut up.
I need $2,000, right? Well, what if in real life it ends up taking 30 person hour, or sorry, 300 person hours instead of 100 person hours? That's $6,000. That's a big difference. If you're going to go to your production manager and say, so I kind of underestimated how long it was going to take us to do this. We need $4,000 more dollars than I told you were going to need. You are probably going to get fired. All right? You are probably going to get fired, okay? Because I guarantee you they don't have that money sitting around, because they're going to have a contingency, but it's not going to be that big, and therefore the show isn't going to happen, and it's going to be because of you. So, so you got to get really good at predicting how long things take, because that costs money in real life. So that's what this is about, and that's it. So those are all the things you're going to learn how to create this semester. By the end of the semester, you got to be able to do all of those drawings. Okay. In fact, that will be your final project, is to create all of those drawings I just showed you.
Are we duplicating this show or a different show?
It'll be a different show, but I'm going to give you drawings that already exist for a different show.
Last semester was like Draft and Chaperone or something. I was wondering if it was going to be, or last year.
Oh.
Wondering if it was going to be the same route.
Yeah, I don't know. I didn't teach that class, but yeah, I'm going to give you drawings that already exist for a show, and I'm going to say, recreate these drawings. Because theoretically, you don't necessarily know what all the drawings mean yet, because I haven't taught you how SAS systems work yet and stuff like that, so I'm not going to have you infer all that stuff. I'm just going to give you a drawing that already exists and say, recreate this drawing. And to the extent that you know what it means, that's great, but I don't really care right now. I just want to care that you can recreate the drawing. Okay? So that's it. I'll see you next week. Yep.